Day by day, year by year, and eon by eon, sun, wind, ice, and water wear away the land. What were once lofty, rugged peaks have been worn down to rolling, gentle hills, and what were once high, unbroken plateaus have been etched into bold monuments of rock. It's these forces of weather, water, and ice that give our planet its present form. Forces that are always attacking, wearing down, and reshaping virtually all land on Earth. We call these processes weathering and erosion. Earth materials are constantly being formed, recycled, and altered in a global geologic process called the rock cycle. In this continuous interplay of forces that takes place both within the lithosphere and on the Earth's surface, rocks are converted from one type to another. Along the way, rocks which once formed by igneous, metamorphic, or sedimentary processes may become exposed at the Earth's surface. It's here, along a narrow zone between the Earth's lithosphere and atmosphere, where rocks begin to disintegrate into smaller fragments in a process called weathering. The two basic types of weathering are physical and chemical weathering. Let's take a look at each. One of the most powerful agents of physical weathering is ice. Try filling a plastic container with water and placing it in a freezer overnight. What do you think will happen? When water freezes, it expands, causing the container to shatter and crack. In nature, the same thing occurs whenever rain or snowmelt seeps into the cracks and crevices of solid rock. At night, the water freezes, expands, and forces the rock apart. This is a process called frost wedging. Water penetrates even farther, and the process continues once more. Each day, the tremendous pressures of frost wedging cause streets to crack and sidewalks to crumble. On a larger scale, the expansion of bedrock can also cause rock to crack and peel like the skin of an onion. Here, expansion is caused by the unloading of a great weight of rock that once lay above this mountain. Living things can physically weather rocks too. Burrowing animals and roots of growing trees take advantage of even the smallest openings, wedging rocks apart. In each case, physical weathering breaks rocks apart and creates additional surfaces for other types of weathering to occur. While physical weathering involves the mechanical effects of frost wedging, expansion, and root pry, chemical weathering relies on the chemical reactions between rock surfaces and their surroundings. From the surface down to depths of several meters, rocks are in contact with moisture from humidity, rain, and snow. Along cracks and fractures, This granite outcrop has decomposed to piles of gravel and sand because some of its minerals have begun to react with water and other dissolved chemicals. In these rocks, iron-rich minerals such as magnetite or biotite combine with oxygen in the atmosphere. This chemical reaction, called oxidation, produces rust or iron oxide in rocks. Could oxidation be the same process that eats away metal and rusts old tools? You can see this corrosive weathering by comparing these iron nails before and after they've been left out in the rain and then exposed to the air over a period of several weeks. In other rocks, acids and other chemicals easily attack minerals and dissolve them away in a process called solution weathering. Limestone, for example, which contains the mineral calcite, readily dissolves from naturally occurring carbonic acid in rain or snowmelt. In fact, there are places where thousands of square kilometers of limestone have been so weathered by acidic rain and groundwater that the landscape has been etched to produce fantastic spires and towers. And the same process that chemically weathers limestone on the Earth's surface can transform tiny fractures into a vast system of magnificent underground caves and caverns. Chemicals produced by growing plants can dissolve rocks too. Lichens and mosses produce mild acids that slowly attack minerals and make the rock weaker. During the past few centuries, people have hastened the rate of chemical weathering, affecting not only rocks, but also buildings, statues, and works of art. The most important product of chemical and physical weathering is the development of soil. Soils, which are part mineral and part organic, serve as the vital link between Earth's lithosphere and its thriving biosphere. As soil evolves over time, it develops distinct layers called a soil profile. In a typical soil, the sea horizon is the first to form and consists of weathered bedrock, the parent material that supplies much of the overlying soil profile. Above it lies a middle layer, or B horizon, containing clay and organic matter leached from above. Finally, the uppermost A horizon, or topsoil layer, consists of sand and silt mixed with dark-colored material from the decay of plant and animal matter. Some soils thick with spongy organic matter form the fertile ground upon which much of the world's food is grown. And yet in other places, where little chemical weathering takes place, soils are thin and depleted of nutrients. Will these soils ever become productive again? Regardless of how chemical and physical weathering take place, they supply the materials that will eventually be transported to another place on the Earth's surface. Earth's varied and dramatic landscapes all attest to the influence of the most common force of change on the Earth's surface: erosion. Gravity, running water, wind, and ice all wear away, move, and transport Earth materials. Let's take a look at each. Have you ever seen highway signs like these? They warn us about the dangers of sudden downward movements of rock and soil, called mass movement. What force pulls these materials down so dramatically? Gravity is the agent of erosion which causes different types of mass movement, some that are rapid, such as rock falls or mud flows, and others that are slow, such as soil creep. Rockfall occurs where weathering loosens solid bedrock into smaller fragments that easily roll or slide down steep slopes. Here, evidence of past mass movement is obvious. Talus, wedge-shaped mounds of jagged rock, accumulates at the base of steep, rocky cliffs in many mountainous areas. Yet on this gently sloping hillside, a more subtle form of mass movement is taking place. Gravity tugs weathered rock and soil down slope in a slow process called creep. In some places, clearing forests, overgrazing, or even fires strip hillsides of vegetation. And when these areas are hit by heavy rains, soil is quickly eroded downhill, often causing destructive mud flows. The second agent of erosion, running water, is also driven by the force of gravity. Running water is such an important erosional force that virtually all of Earth's land areas have been shaped by the work of rivers and streams. In fact, the Grand Canyon of the Colorado River formed this way, carving a 1,500-meter deep canyon in less than 5 million years. How can a substance as soft as water accomplish such a mighty feat? If we look closely at how running water erodes earth materials, we find that energy from moving water carries particles ranging in size from the smallest flecks of clay to boulders as large as automobiles. Like natural conveyor belts, streams carry these loads of sediment downstream. High-energy streams move enormous rocks and carry large loads of sediment. As they do, the mixture of churning water and sediment grinds away a stream's channel, cutting deeper and wider into the valley floor. We can demonstrate stream erosion by mixing angular rock fragments in a container of water. Vigorous shaking, like the high energy of a fast-flowing stream, causes rocks to collide with each other and wear away bit by bit in a destructive process called abrasion. Over millions of years, downcutting and abrasion wear away the Earth's surface, first by carving deep V-shaped valleys, and later by widening them into broad floodplains. Along coastlines, erosion takes place where powerful waves abrade rocks and transport sediment. What evidence of erosion by water can you find where you live? Wind is the third agent of erosion. It circulates moisture in the atmosphere and whips the ocean's surface into frothy waves. On land, winds lift and carry loose sediment away in a process called deflation. In places with little or no vegetation, desert winds easily erode tiny fragments of sand and silt, leaving behind a layer of larger particles. Wind also abrades and scours objects, often sculpting desert rocks into eerie pedestal-like shapes. Each year around the world, wind erosion removes billions of tons of valuable topsoil from farms and fields. What are the effects of this type of erosion on all living things? The fourth agent of erosion, ice, can sculpt the land with dramatic results. For instance, 10,000 years ago, California's Yosemite Valley lay under a sheet of ice more than a kilometer thick. The ice, of course, has long since melted, but the erosional features it left behind have given Earth scientists valuable clues about Earth's past. High waterfalls, flat-floored valleys, and ridges of jumbled boulders. What do these clues tell us? When winter snows accumulate faster than they melt, the weight of top layers presses the bottom layers into a dense form of ice. A glacier is born. As this actual time-lapse film shows, the enormous weight of thickened ice causes the entire glacier to flow slowly downhill. Like rivers of ice, valley glaciers are pulled by the force of gravity, flowing from high mountain snowfields into broad valleys below. Boulders and other rock fragments, trapped along the glacier's edge and bottom, act like grit on a giant strip of sandpaper. The mixture scrapes and polishes the bedrock, sometimes gouging out long, parallel grooves into solid rock. So powerful are these